Hello, ladies and gentlemen, and welcome to this webcast on patient-specific morphing of musculoskeletal models. We are going to talk about methods today for changing existing musculoskeletal models to become patient-specific, much like in the image that you see just before you, where we have an original model on the left-hand side and a morphed model on the right-hand side. So what I'm going to be discussing today is how we accomplish this type of model transformation. My name is John Rasmussen, and I am the presenter of this webcast. And next to me, I have Søren Tjørholm. He is today playing the role of the host. So he's trying to keep the ship afloat technically while I give a presentation. This is a WebEx webcast presentation, and one of the nice things about webcasts compared to ordinary live presentations is that you don't have to worry about disturbing the presenter if you ask questions. So if there's any question that you would like to ask during the presentation, please don't hesitate, just go ahead and ask it. You can do that by clicking on the little question mark in the lower right hand corner of your screen. If you do that, you will see a question and answers panel popping up, and into that panel you can ask your question. Please make sure that when you submit the question, that you send the question to host, presenter, and panelists. What happens then is that the question will go to Søren Tjørholm and me, and if it is an easy question, then Søren Tjørholm will answer it directly in your question and answers panel right away, and if it is a question that seems to have any general interest, then we will postpone the answer of the question until the end of the presentation, and then I will answer it orally here for everybody to hear. With that, let us get started on the actual webcast. And the first thing I'd like to introduce to you is different scenarios of scaling that we might want to do to musculoskeletal models. These are the three different scenarios that you see in front of you, and the first one is what we call the detailed level, and in fact that has always been possible in the Anybody modeling system because the models are completely open. So you are able, actually, if you have all the parameters of the model that you need, you're able to go in and change anything that you like. There's also a scaling on an individual level, so this is something that would be useful, for instance, to scale a model to a particular sports athlete, or if you do gait analysis of a particular individual. And there's also an overall population level on which you can scale the models. Now, the two latter forms have been covered in a webcast that is available pre-recorded at anybodytech.com. If you go in there, you can listen to a webcast about that issue. But today we are going to focus on the detail level, but in a slightly different way from what I mentioned initially. Scaling on the detail level, as I said, can be done if you have all of the data of the model. But models contain such a large amount of data that it is actually not usual that we are able to collect all the data for a particular individual for creating a completely individualized model. So in order to make individualized models for specific patients, we have to take the information that we can gather from information processing techniques, and here I am particularly thinking about scanning techniques, and then we need to use that information to modify the existing models to as high an extent as possible so that they become individualized. And this is what we're going to look into today. Now, again, I'm going to take out this picture just to give you an idea about what this is about. On the left-hand side, you see a picture of the standard model in anybody of the lower extremity. Actually, just the hip region of that model. So you see the pelvis and you see the upper part of the femur. And on the right-hand side, you see a patient-specific model. And although there are definite similarities between the two models, obviously you can recognize the pelvis and the femur in both pictures. You can see that there are also quite significant differences. If you look at the right-hand side pelvis, you can see that there are definite shape changes, different shapes on the pelvis on the right-hand side compared to the standard pelvis on the left-hand side. You can also see the femoral head has been replaced in in the picture on the right-hand side, so we have inserted an artificial hip, so a hip prosthesis has been put into this model. And of course, these are changes that will affect how the model works, and if we want to do a patient-specific model, which might be used for predicting the outcome of such a surgical procedure, then we have to individualize the model from what we have on the left-hand side to what we have on the right-hand side. So let's look at the ingredients that we need in order to accomplish this transformation. So what we need is some sort of scanned patient-specific data, which can typically come from MRI or CT scans. This type of data comes out of the scanner in a file format called DICOM usually, and it is basically just a stack of images, cross-sectional images of the different bones. And in order to proceed with those images, we need to take them into some specialized software, which is developed particularly for processing such data. Examples of such software would be Minutes or Simpleware, or Amira, I can also mention. Once you have the data in this specialized software, you can do various manipulations to it in order to acquire the data that are necessary to create a scaling. And these data you can then import into the Anybody modeling system and into the AnyScript managed model repository. And I'm going to go through the process of doing that with you. So I want to introduce first the idea of radial basis functions. This is a mathematical technique that we have employed in our models in order to accomplish the morphing. And radial basis functions, to explain what they are, the best way is actually to explain it by means of a sort of a spline. Splines are curves, smooth curves in the plane or in space, and they are parametric curves, so you can think of the parameter space as a straight line at the bottom of this picture, and you can think of the actual spline that we want as a curved line on the top of the picture. Now, the way these splines are functioning mathematically is that there are points, so-called knot points, in the parameter space at the bottom, which corresponds to the actual points on the spline at the top. And in between those actual points, we have blending functions which are taking care of interpolating between the points that we have given. So if I try to make pictures of these interpolation functions or influence functions, you can see that they have influence in a certain region about their own locations. And in between those regions, what you get is a mix of influences from the neighboring control points. Now, if we extend this idea to 3 dimensions, then you can imagine that we have a number of points in space, and each of these points designates a certain location. And locations in between those points are then determined by blending functions that originate from these points and which have a weight that corresponds to the distance from the points, the spatial distance. And that is why they're called radial basis functions, because they are the radial distances that determine the influence of the different points. Now, I'm going to do a 3D demonstration of how this works in Anybody, and then you will understand it very easily, I think. So I'm just going to close down my presentation, and then I will open up the Anybody modeling system, and I will load in the scaling or morphing model that we can use as an example. So having done that, having loaded the model, I'm just going to open up a model view, and we can look at the model, and I will make this occupy the entire screen. So what you see here is actually 2 pelvises on top of each other. The 2 pelvises are very similar. Actually, they are the same. It's two of the same bones on top of each other. So you can see that we have sort of alternately the blue or the red surface shining through here. So they're actually the same pelvises. The shape of the red pelvis and the blue pelvis are actually subjected to the location of those points that you see around the model. If we look closer at those points, you can see that 8 of the points are configured sort of in a box that surrounds the model. And then the remaining 2 points, we have 10 points in total, are placed at the acetabulum on each of the sides of the pelvis. Now, what I can do now interactively here in the system is I can start morphing one pelvis away from the other pelvis. And I do that by grabbing these control widgets that I have in my model view, and by means of those widgets, I can then pull the points in different directions. So let's say I want to take the point up here, and I want to pull it slightly inwards to make the pelvis more narrow. I can do this on one side, and what happens is that now the red surface has moved compared to the blue surface, and I can do the same thing on the other side. So you see how the red pelvis is sort of following the displacements of the points that I'm giving here. Now I can also take another point. I could take this one, for instance, and displace in some direction, and again I get a different pelvis. I can rotate it around a little bit, and maybe I can take the point here in the acetabular, and maybe I can move that down a little bit, and then again we get a different and more elongated shape of the pelvis on the left-hand side. So you can see the idea now that the pelvis, the part of the pelvis which is in the vicinity of the points that are moving, is influenced by those points, and the part of the pelvis which is away from the points is not influenced by them. So that way I can obtain a sort of a local morphing of the bone in the vicinity of these points. Now, the really, really cool thing about radial basis functions as a morphing technique is that I can have a point cloud. So the box configuration of points that I have here doesn't need to be like that. I can have any number of these control points, and they can have any configuration at all. It doesn't even need to be a regular configuration. It can just be points that are scattered in any way in the space occupied by the pelvis. The only thing that has to be valid for this is that the radial basis function scaling works best as an interpolation, and it does not work very well as an extrapolation. Now that means that I somehow the control points that I have and which I can change here have to be points which are somehow where the convex hull of those points is containing my geometry. If I have too much of my geometry that is sticking out of that convex hull, then typically that part of the geometry will not be scaled correctly according to the position of the points. Now, having shown the basic idea of this, let's see how this technology can be used to create patient-specific models. So I'm going to go back to the presentation again, and we can proceed to some observations about the morphing as we have just seen it. Now, you can see that what happens is that morphing is actually a way of mapping one set of points to another set of points. And that means that I have two sets of points. I have what we can call an origin set of points that define the original geometry, and I have a set of target points which are defining the geometry that I want. And notice that these are finite sets, so I don't need very many points actually to create a rather detailed scaling. So they are finite and actually quite small sets. What happens with the radial basis functions then is that they take the differences between those two sets of points, and then they create a mapping from one set to another. And that mapping we can then apply to all of the other points that we have in the model. And all of the other points in the model will then be subjected to some blending of displacements depending on where they are located compared to the control points. So that is really the idea behind this. In order to understand how this works more precisely for creating patient-specific models, we have to look into how models are actually defined in Anybody. So typically, when you see an Anybody model, you might see a picture like what you have here on the left-hand side, where you see realistic bone shapes, and you see muscles surrounding the bone and also inserting on different locations of the bone. But in reality, the internal representation in Anybody is more like what you see on the right-hand side, where you see these pins sticking with round heads sticking out of ellipsoids. And the pins are actually points that are defined on the model. And what we want to do is or what the model does is that it uses these points either as joint locations or as insertion points for the muscles. And that means that if we start moving these points around, then what we actually also move the locations of the joints, and we also move the insertion points of the muscles. Now, the idea is that muscles are inserting on the surfaces of the bones, and they typically influence the bone growth because the muscles are exerting forces on the bones, and the bones are adapting to these forces. So many of the condyles and other prominences that we see on the bones are actually there because of the reinforcement of the bone that is necessary to carry the force of the muscle. And this means that there is an intimate relationship between the shape of the bone and the locations, the insertion points of the muscles. So the idea here is that if we can get information from the scanned data about the detailed shape of a bone, and we then can compare those detailed shape features from the patient's bone and back to the original bone in the antibody model, then we can use those paired features or points and bony prominences. We can use those to create the radial basis function mapping, and we can then subsequently route all of the points in the model through that mapping, and that way we can create a patient-specific model in which all of the muscles and joints and so on is moved around to reflect the geometry of the patient. So I'm going to go through the actual steps that are necessary in order to make this happen in anybody. And the first step is that you locate into anybody, or you load into anybody, the original model that comes from the anybody managed model repository. And then in that model, you locate your bones. You can do that in the model view over here. You can see I have highlighted the pelvis in the model view here. And when I highlight the pelvis, I can go from the pelvis and locate the pelvis in the tree, which is what I have over here. I can then right-click on that surface object in the tree, and I will get a context menu from which I can choose Export Surface. If I export that surface, I will obtain an STL file with the surface information. Now, this STL file I can then import into my image processing software, so into Mimix or Simpleware. And I also import the DICOM images that I have from scanned data, from the CT scan or MRI scan. And then I have two pelvises. One pelvis is the original one from the antibody model, and the other one is the patient-specific pelvis. Now, they will not be located in the same coordinate system initially. So we have to use the registration feature of the image processing program to place those two and align them and rotate them in such a way that their coordinate systems become the same. So that's what we have on the next picture here. So now you see we've taken these two basically quite different pelvises, and we have located them on top of each other as well as we can, based on the shape information that they have. And this process of registration can take place in the image processing software. Now, having done that, we will have to use the facilities again in the image processing software to point out specific bony prominences on the two different bones. So, for instance, we can take the ACES point here on one bone and one on the other bone, and we can say these 2 points correspond to each other between the original bone and the patient-specific bone. And other bony prominences we can take as well, and we can pair them up between the original and the patient-specific bone. And it's important here that we need as many of these points as possible, as many points as we can reliably identify between the two pelvises, and also we need enough of these pairs of points to encapsulate the entire bone, or at least the part of the bone that we are interested in scaling. Now, when we have done that, we will have to take those points and we have to export the 3D coordinates of those point pairs into a text file. And that text file we can then import into the antibody modeling system. So in the antibody modeling system, we will have two lists of points, one from the original from the original model, which is called point 0, and one down here, point 1, which is from the patient-specific model. Now, with these 2 points, those 2 sets of points, we can wrap those into an object we call any fun transform 3D RBF. And what this object does is it takes the 2 sets of points, and then it creates an RBF mapping between those 2 points. Now, the RBF mapping can then be used to scale all of the other functions, all of the other points in the model. So everywhere that we have a point in the model that has some nominal coordinates like these, for instance, in the original model, we just wrap those into the scaling function, and then this point will be transformed over into the patient-specific model. It's not as cumbersome as it looks because the Anybody Managed Model repository is already set up in such a way that all of the points in the model are referring to a virtual scaling function. And by virtual, I mean that this scaling function can be replaced, and we can use as that scaling function the RBF scaling function that we have just created. And that means that we just have to specify the function, and then automatically all of the points in the model will get scaled through that scaling function, and we will obtain our patient-specific model. And that way we can obtain something like what we have here. So if we look closer on these 2 pictures and look a little bit at what's going on and what the operator has been doing, you can see the picture on the left is the original geometry, and we can some of the things that are interesting. One of the things that is particularly interesting here is that you see on the left-hand side you can see some muscles here, which are probably supposed to insert on the greater trochanter, but which seem to end in free air somewhere. The reason why this is happening is because in the 20 lower extremity model, which is the one we're using here on the left-hand side, the bone that we have here is actually not yet the original one, and therefore some of the muscle data that have been recorded from the cadaver specimen do not exactly fit the bone. So what the operator has done here is he has said, okay, I'm not going to take the bony prominence here. I'm going to take the actual insertion points of the muscles, and I'm going to use that as the original point. And then obviously over here in the patient-specific model, he has appointed the greater trochanter as the target point. And this means then that after the scaling function, after all of these points have been routed through the scaling function, these muscles will insert exactly on the patient-specific version of the femur exactly on the greater trochanter bony prominence. And it's the same thing with all of the other bones. The actual bone models here on the left-hand side are not scaled versions of the ones that you have on the actual bones on the right-hand side are not scaled versions of the ones you have on the left-hand side. We could actually do that, and if we did that, we would get something on the right-hand side that would be similar to what we have here, but it would not be as accurate as the real bones that we have inserted here. So notice that when we have the original data from the scans, which we have in case of the bones, we might as well use those bones in the model. But what is really important here is that all of the muscles are now inserting on the correct places on those bones, because all of the muscle points have been routed through the RBF mapping that comes from comparing those 2 sets of bones. So there is a tutorial that you can look into if you are a user of the Anybody Modeling System. You can go to help, and from help you can open the tutorials. And in the tutorials you find a scaling tutorial, and lesson 3 of that scaling tutorial is a rather brief version of what I have been saying here. Now, probably we will extend this somewhat in the future, and we will also probably extend the facilities for RBF scaling somewhat in the future. But right now you can get a very good flavor of how it works by looking into this tutorial. The final remark is that the RBF scaling is not primarily a method to morph a standard bone to a patient's bone, although the method does allow you to morph the bones. But if you have the real data for the patient's bone, then you simply insert those into the model. What the RBF scaling function primarily does that is extremely useful is that all of the other data in the model, which are geometrical data that somehow depend on the bone geometry, will be scaled according to the bone with the RBS scaling that comes from comparing the two bones. So with that, I'd like to thank you very much for your attention. If you want to know more about what I've talked about here or about Anybody in general, you can go to anybodytech.com. There you can download the software and you can request a free demo license for the system. There's a little bit of processing time, and then the demo license will arrive in your inbox. You can also go to the website called inscript.org, which is a discussion forum and a wiki and a model repository where we are keeping all our models in an open source format. And also there are very lively discussions going on about modeling issues in Anybody. Finally, there's the webpage anybody.aau.dk, which is the homepage of the Anybody Research Group, and there you can find information about research events that are going on. And with that, I would like to end the presentation.